Welcome to our second keynote of the afternoon. We've the number of people entering the session have just slowed down now, so I think we're probably about ready to go. So I'll just get things started and we can hand over to Tom. So thank you for hanging in with us for the day. Don't forget to check out the virtual delegate satchel before you go this afternoon, or that will also be there later when you might come back to watch sessions in future. Tom, can you just nod and confirm you can see my screen just to make sure everything's good? Thank you. Our afternoon keynote sponsor is Corwin, and so there's a video from Shane Crawford who's just going to say a few words about their programs. So please have a listen to this.
Welcome back to this afternoon session as we continue to explore meaningful mathematics in a supportive, hands-on and engaging series of workshops. Mathematics has long been a passion of mine due to mentors like Dr. Kath Pern, who has inspired the rewarding work I do today in partnering with educators to explore the right mathematical approaches at the right time. Preparing for today has created the opportunity for me to reflect on those hands-on, practical learning experiences that are rich in play and inquiry. I can remember giving each of my 5-year-old students a bean to plant as a mathematical task to observe, measure, and record the growth of their beans over time. You know that excitement and chaos as the children decided on where to plant their bean. There was extensive variability in the decisions and choices the children made. Some planted in the designated vegetable gardens, others in the sandpit, so deep that the bean was never going to see the light of day. Beans carefully planted just above the surface, and others in the clay soil next to the slide in the playground. Every child brought their own skills, knowledge, and experiences to growing their beans. Some were overplanted, some were watered the wrong way, others were left to their own devices, and my highlight was the child who diligently every morning dug their bean out of the ground to see if it was growing. Imagine the learners you influence every day. What are the conditions and experiences you provide so that your learners can flourish and show growth in the form of progress? As educators, we have a multitude of programs, practices, and Pinterest examples to support our learners. Part of my role at Corwin Australia is partnering with schools and educators to make decisions about the practices undertaken so that every child learns not by chance, but by design. We equip educators with the current research, intentional instruction, meaningful tasks, rigorous experiences, and relevant examples to use the right approach at the right time for students aged 3 to 16. If you would like to know more about visible learning for mathematics or how Corwin partners with early childhood centres and schools across Australia, please have a look at your virtual satchel to find out how we can support the learning progress of all our beautiful beans.
Thank you.
Welcome back to this afternoon session.
And I think that Shane might be with us in this session. I'm not sure, Shane, if you are there, but you're most welcome to message Shane as well if you'd like more information. I know he's been in and out of sessions during the day. So I'll now introduce Tom and hand over to Tom for his keynote. So I know Tom pretty well, actually. He was on the board of MAV for a little while, and Tom's done a number of projects for MAV and producing content and delivering professional learning over quite a period of time. Tom is a passionate educator who's driven to helping both students and teachers to enjoy the experience of working mathematically. He's currently completing his PhD, exploring how productive relationships are formed between teachers and their students. When he isn't studying, you'll find Tom working as a casual relief teacher in classrooms around Melbourne. So he enjoys putting his ideas to the test to ensure they are robust and hold true under a range of teaching conditions. Tom also works with teachers and school leaders across Victoria as a consultant to help both primary and secondary schools implement an inclusive and engaging mathematics curriculum for all students. Tom's an avid believer that everyone can enjoy mathematics and that the key to achieving this is often in our delivery. And I know Tom is a great presenter from the point of view of working with teachers, and he's been doing some of the Mylands work for Department of Ed last year, and his presentation style and activities he was developing were very well accepted and taken on board by teachers. So I look forward to your presentation, Tom. Best of luck for your presentation right now. Go for it.
Thank you very much, Peter. I appreciate the intro. No pressure, of course, but I'm looking forward to what will be an exciting, hopefully, presentation for everyone. Before I go any further, though, I'd like to sort of take a step back and tell you a story of sort of how I've come to this point, sharing this here with you today, talking about manipulatives and choosing the right types of things to use with your students. But to go back and do that, I'm going to need to change the camera angle. So bear with me a second whilst I do that. And I've just got to get into the right one. Okay. Just got to find the right camera, sorry. Okay, yep, so can everyone see my two chins there? Is that all right? Give us a nod if that's correct. Yep, thank you very much. All right, so this actually it starts outside of this room. And I'll just show you. So I've actually started collecting like a whole lot of equipment. There's my table tennis table. And here's my storeroom full of maths equipment, which is, I guess, a cause of absolute jealousy for all my friends that aren't maths teachers. I'm sure they'd love to have all of that. And then if I keep coming out, there's my big bear that I made a couple of years ago for a party. It's not really that relevant, but if I come over here as well, some more maths equipment, lots of games and all that kind of thing. So as I said, cause of massive jealousy for my friends, but probably more frustration for my partner, who is very patient putting up with all of that stuff lying around the house. So why do I share that with you? Well, I want to tell you a little something else, but I'm going to swap my camera back again. So what happened was I've collected all this equipment just because I've always been interested in how to represent maths to students so that they can make sense of it when they look at it, and it gives them an understanding of what's actually going on. And so that's all the stuff. But just to give you a bit more of a background, as Peter said, I do CRT work. I'm actually doing the tutoring stuff this year as well. And I'll show you what I look like when I'm walking around the schools with all my stuff. Let me just get this up and running. So what happened is I've got all this equipment and I find myself walking around schools trying to carry it all everywhere. So if I share my screen with you, I'll show you sort of what it looks like for me and how my life looks like when I am doing this. So let me share that for you. You should be able to see the screen. Can we see the PowerPoint? Yeah, excellent. So here we have, this is me here walking around with the big suitcase. Now, every time I'm walking around the school, or the schools that I'm at, people seem to ask, or pre-COVID, they seem to ask, whereabouts are you going on a holiday? So if I had $1 for every single time that I got asked that question, I probably wouldn't even need to work, because it does come up quite a fair bit. But now, since COVID's kicked in, people seem to ask things like, is that a bomb in there, or have you got a dead person in there? I don't know where people's minds have gone to, but it certainly has changed because of COVID. But what I found last year in particular was that it wasn't like I wasn't able to go around with all this equipment. For one, it's not a great idea to go to different schools and get students touching all the same stuff. And the other thing was I obviously wasn't in school. So I was faced with a challenge to try and deliver the same kind of thing that I had been doing with all of these hands-on manipulatives, but in a different way. And that, of course, was a challenge for me. And so I was doing all of this remotely, and I started creating some animations. All right. But before I do go into the animations, I want to talk about some of the other stuff that I have, or the reason for why I do this. Okay. So the reason why I have all this equipment and I like to get students using it is because I really think it's a great way to develop their understanding. And I think of learning as being a bit like paper mache. Like, you can get a bit of paper, cover it in glue, and then stick it on. Now that's how I see these, or using equipment, working. That is, when you use or when you teach concepts in different ways, using different pieces of equipment in many different examples, it's like attaching lots and lots of pieces of glue and then sticking it to the paper mache. Whereas if you teach the one thing in the one way, it's like attaching one little piece of glue and having it just attached like that. And then eventually over time, as we go by, we add on another piece of glue. If we only teach it in the one way and we attach it to the prerequisite knowledge that we need to know, it's like attaching it with that. And you can see here, it sort of starts, it doesn't attach quite as well. And we can keep doing that and keep doing that. But what happens is this here is a lot harder to take off when we attach it with more glue. That is, it's harder to lose track of or forget when we've attached this skill or this knowledge and understanding in a number of different ways. Whereas when we attach it just in the one way and we show only the one way of actually doing something, we can see here that things can start to fall off pretty easily. And so that's why I go around and I use all this equipment, and I use it not just for primary school students, but really actually more so often for secondary students. And people worry about, is it a student's embarrassed or anything along those lines? But what I find is when I use equipment with an entire class, the student, and then give them the choice to actually whether or not they want to use it, the students actually often engage with it and use it well. And I never have really any issues in respect to that. So let me just wash my hands off a little bit for a second whilst I do that. Regret with the glue. All right, so let me just share why I do this. So I do this stuff, like I said, for how I see learning, and I believe that attaching the learning in as many different ways as possible helps to form some form of mathematical intuition. That is, it helps to get students to understand or make sense of what they're seeing so that they can then take it and continue to apply it moving forwards. Whereas if we teach just using things like algorithms or the single approach over and over again, it doesn't help with that mathematical intuition as much. And I had a look at the etymology of intuition, and this is what came up. If we go, so intuition comes from the word intuere, all right? So that's Latin, to look at or to consider. And intuere can be broken up into two parts. The first one is in, so at or on is Latin for at or on, but tuere is the bit that I'm interested in, that is to look at or to watch over. And the word tutor actually comes from the word tuere. So intuition is actually somewhat linked to tutor. And in some ways, it could represent an tutor. So why do I do this? Let's just sum it all up and bring it back. The reason why I have all of this equipment and I go in and I use all of it is because I strongly believe that this stuff here and using equipment and representing maths in many different ways is about helping students to develop an intuition, mathematical intuition of what's going on so that they can make sense of the mathematics and they can attach their learning in as many different places as possible, much like what we saw with the paper mache here. So this is what I ended up creating in going into lockdown and remote learning 1.0, 2.0, 3.0, and 10.0 or whatever we're up to now. It's these animations. So I tried to create things which I couldn't use, obviously, hands-on manipulation. So I wanted to demonstrate math concepts in other ways and ask the question, what's happening here? So as you can see here in this video, there's an animation showing a parallelogram is the same as an area of a rectangle. When you know your height and your base, you can then figure out the area of the two just by moving it across like that. And then I built on this and I ended up coming up with other animations as well. So here's one for how to find the area of a trapezium. All right, you can see here it's much like the area of a parallelogram, and all you've got to do is rotate it around. So then for you go the area of A plus B times the height and divided by 2. Just let you see that one again. Here's one for the volume of a rectangular prism. I found working with Year 9 students last year that they didn't actually even know how to calculate the volume of a prism. They had no idea what a prism really was or how it operated. And so through doing these animations, students were able to see that, and then they were able to much better predict how it was going or how to find the volume moving forwards. And in fact, I find showing this animation now much more helpful than at times getting them to create it, because it's a lot faster and they can see how it builds moving up. So it's that multiplicative thinking coming through. And then that led to a whole bunch of other animations, which I'm not going to go through all of them now, but you can see here how there's many different mathematical animations that represent different maths concepts. And what I found when doing these, so I started to share them publicly through my Facebook page, engagementmathematics.com, so the Facebook page for it. And of course, when you share something like this on social media, you've got to have a pretty thick skin, because there's going to be times where people don't agree with you, or they're going to throw things back and say, oh, why didn't you do it like this? And it was actually really good because I got a lot of feedback from it. But what it actually made me do was really think deeply about what it is that I'm actually wanting to create. So if I want to represent a mathematical concept, how am I going to best represent that with no words or limited words, and just showing a picture or an animation? And how am I going to do that without building up or without creating misconceptions? And what representations are good to some points, but then are no good beyond that? So what I figured out, or what I learned through doing this, was that there are a number of things that we use within our classes that I know when I was a teacher full time, I didn't have the time to think about, right, well, what's the best way to do this? Or what are the limitations of this model? I go and I just do it, and I'd be often chasing my own tail. Whereas through going through this process, it really helped me to figure out, okay, well, what are these mathematical models that I'm using? What are these models that I'm using to demonstrate to students? What are their strengths? What are some of their limitations? And also, are there any misconceptions that they might be forming through using these? So that's what today's presentation is about. I've got about 45 minutes left, and I'm going to break it down into probably into 4 of the big ideas. That is trusting the count, place value, multiplicative thinking, and partitioning. Hopefully I'll get through all of those. We'll wait and see how it goes. If you've got questions, feel free to put them into the chat, and Peter will make note of it, and we'll come back to that at the end so I can help out with answering those. So please feel free to ask them in the chat. So when it came to me making these animations, there are 3 main questions that I would ask, and those were the ones I sort of touched on before. That is, what does the model demonstrate well? All right, what is it actually going to demonstrate really well? What are some of its limitations? So no model I've found is actually perfect for demonstrating everything. And then also, are there any misconceptions that it might create through demonstrating this model without any words or anything along those lines? And that was the main one that I had to think deeply about. You know, you come up with an animation, but it would be a matter of, okay, now what possible areas could this make students think is true that aren't actually true in all instances, which was the real challenge. So the first of all is we'll look at some supertizing in terms of some models that you can use, or for trusting the count, models that you can use to help get your students to understand the part-whole nature of number. The first one that I've come across recently actually are these pretty cool little bracelets. So you can get students to create their own bracelets with beads. And can you see those all right there, Peter? Yep. So what you can do with these is you can use any number. So I've got 8 beads on here, I believe. And you can then use that to show systematically all the different ways that you can make 8. For example, I can make 8 with a 1 and a 7, like that. I can make it with a 2 and a 6, and you get the idea going through there. So I quite like these in terms of how they can be used for students, and also they get a nice little memento when they leave as well. But the different ways that all the different ways that you can systematically work through and make the numbers. And you can do that for any number as well. So you can get students differentiating quite easily by, if you've got a student who's a bit stronger, you can give them those numbers up to 20, whatever you want, and then explore that. And here's another one with, say, 10 beads as well. So that's one of the models that I quite like. In terms of that, though, one of the strengths of it is, well, there's flexibility in terms of what numbers you work with. So you can have any number really. You probably wouldn't want to go much beyond 20, but you can use any number. One of the one of the weaknesses of it, though, is that it really doesn't allow for the less than. So that is, when we have a look at this one here is, what have we got here? This is 9. It doesn't really show that it's one less than 10. So understanding the part whole nature of number is really about understanding, the different parts to make it up. But part of that is, 9 is 1 less than 10 as well, and it doesn't show that as such. So then that's one of the limitations. So therefore, in come another model where it might be help to demonstrate that a bit better. So that might be, of course, something like the 10 frames, which we've all seen before. Now, as I go through and show these as well, feel free to put in other weaknesses or other limitations in the model or misconceptions that you found used as well into the chat. But you can see here that the 10 frames, they're quite good at using, at demonstrating this less than idea, all right, especially a 10. But one of the limitations of it that was really good with the other model was the fact that you can only really do the numbers to 10, first of all, whereas the other one, you've got a lot more flexibility in what you do. So therefore, that's where you might go for one of those. So it's about choosing, obviously, which model works best for you. Then, of course, you've got the supertizing cards, which I'm sure everyone's seen and used before, where you essentially you flash the card for a couple of seconds, they have a look at it, then they put it away. And then you ask students, what did they see and how did they see it? So with this, the key here, what I find here in terms of a limitation for this model is that it kind of can build up this idea that to be good at maths, you've got to be quick at maths, which isn't obviously what we want. We want students to be able to think deeply. So the important part of asking or using something like this is the questioning or the conversation that takes place afterwards. That is, what did you see and how did you see it? So thinking about any kind of model that you use and what are possibly some misconceptions or some potential problems that might arise from using that model. But the advantages of having something like this is, once again, they're more flexible. It shows the numbers a bit more randomly than the 10s. So I feel like it's probably the next level up in terms of difficulty, and going from there. Then you can use something along these lines, which I quite like, and that's the splat stuff coming from Steve Wyborny's work. And that is, you've got 8 dots here. Some of them are covered up by the blank or by the ink splat. How many dots have you got underneath the ink splat? So it's, once again, it's building that part whole nature of number, but it's through doing through using subtracting to be able to do that. And I'll show you a couple of just where you can take this as well. So you got 16 here, so it's the same kind of idea, but we've gone a little bit higher. If we go to the next one, this one I quite like because we're starting to move into some multiplicative thinking, but also into the beginnings of algebra, really, because you can have a look here and you can say, well, I've got 18 dots here on this page, and out of those, so you can see here that we've got 1, 2, 3, 4, 5, 6. I've got 6 dots that aren't covered, and then underneath each one of these ink spots are the same number of dots. So each ink dot covers the same number of dots. All right, so so the splat cards, yep, they come from stevewyborny.com. I've got some slides, and they'll be in the slides for you too, so you'll be able to get a hand on that. All right. Then we've got, so you've got 2 different colored splats, and each color has a different number of dots under it. So you could say I've got 15 dots altogether. What might be under the blue? What might be under the white? And it's bringing different ways of bringing the numbers together. So they're a really, really good way, and you can see just how far these are taking. Once again, the pink ones have the same number of dots under it, and the white one has a different number of dots. What might form this? So you can see here the algebra that you're starting to think about. You're starting to move into solving equations and whatnot as well. And then this one here, I've got 7 counters underneath. All the counters are made from 2s and 4s. So that means there only are 2s and 4s under here. And the total needs to come to 20. What might it be? So you can see here that, once again, there's a whole bunch, there's a lot of places that you can do that. So it starts off as trust and count, but then it's starting to move, and you can take it quite a fair bit further based on this. Then the Reckon Recs. So I'm just looking at some of these, and for me, for a long time, I looked at these and I thought, well, what is it why do we have 2 colors? Why would there be 2 colors on these Reckon Recs? Has anyone got any ideas? Do you want to put it into the chat if you do? Any idea as to why there might be two colours on the Reckon Rex? Easy to distinguish 5 and 5, yeah. So we can see here that there's 5 here and there's 5 here, yeah. All right. I looked at it and I started thinking about the whole idea of doubling and so work with rounding. Okay, so you can see here. So work with rounding. So if we've got 5 though, 5 is meant to round up, which I'll come to rounding in a second because rounding is an interesting one too. So there is some, like if you got 6, you can see the rounding's easier. Yeah, doubles. Yeah, and that's the one that I thought was the bit that came into. If you've got double 6, we can quite quickly see that that's double 5 and 1 more. Or in other words, we know double 5 is 10 and double the 1, it would be 2. So therefore double 6 is the 12. If we've got double 8 or 5 and 3, double 8 is going to be 16. You can tell just by looking at this that this is a really nice and neat way to start building up this understanding of doubles. Yeah, and base 5, bridging the gap. Yeah, nice. I'd be interested, Sarah, to hear a bit more about that if you want to put that into the chat. I'm not quite sure, but yeah, I like it. Thank you. And then why would you use that over this? Well, this abacus starts to really begin looking at things like place value and whatnot as well. Once again, though, as I said, when looking at all of this stuff, it's looking at it through a lens of, okay, well, what is it that it shows and does well? What are its limitations? And then what misconceptions might it form? All right. Things like the abacus, you might find students that keep counting by ones, whereas the idea of the flashcards is to build up students' recognition of, 3 is 3, 5 is 5, and be able to go from there. So there are different benefits in using each one. It's about using different ones to represent the different things that you want to show students or that you want them to get out of it. And it's thinking about, okay, well, which one's going to be the best one moving forwards? Let me have a look now at, we'll go into some place value stuff. If I go place value, the first place to start would be obviously getting students to make a whole bunch of 10s. So if you put out a whole lot of counters, getting them to make 10. Now, this is a great place to start, but you're going to end up having your kids get really frustrated and sick of you if you keep asking them to make 10 over and over, or make hundreds, or count. If you put out all of these counters, to make them count all of them over and over again, they're going to get pretty sick of it. It's about, you've got to give them time, obviously, to make the 10s and to build this idea of 10 of these is one of those. And I like to use, for example, having, you might have 10 of these and swap them over for a different type of counter. I've used 10 of these before and swapped them over for a car, but it's that process of, getting to make, you have 10 here, swap it over for one of these. So 10 ones becomes 110, and then they know that. So whenever they see 110 here, they can go, okay, well, I've got 20, and I know that I've made those two 10s, so therefore I know that is 20, that represents 20 because I've gone through the process. But as I said before, the limitation of this is you're going to get people getting pretty frustrated with you if you keep going through and getting them to count over and over and over again, because there are more efficient ways of doing so. So that's where obviously things like MAB comes in. So when I think about MAB, we've got some here. Hopefully you can see that all right. And I'll just grab some here. Now, no doubt you all use this pretty frequently. But I had a student in year 7 the other day who I was going through, and I had assumed, I made the assumption that they knew what each one represents. And even though I'd gone through it, I hadn't really gone through it enough with this student clearly, because when I was going through and asking them about, what each one represented and trying to rename, they had no idea that they were actually calling this one, and they had no idea what this was. So that's where we need to make sure that we give students plenty of opportunities to build or to put together 10 or make 10 so that they can see that, okay, well, 10 of these units, or 10 of these ones, sorry, they're called, make, and show them that. And then therefore 10 10 to make 100. So this one, these have their limitations particularly if students don't understand that 10 of these happen to be one of those. There needs to be a lot of work and development in terms of understanding to really get their heads around that. From there, well, what about some other types of things? Well, there's number expanders and things like that. So if we go, I'm going to grab some number expanders. I've got stuff everywhere here. So we can see here, if I've got my number expanders, these ones are really quite good in terms of building up from there as well. So for example, I might write 3,642. Okay, so I'm just reading the things as we go through. So it's 3,642. These are really quite good for renaming, just like we've done with this stuff here. So I can rename, for example, I might say that I've got 2 10s here, or I could say it's 21s. And these number expanders, as you've probably seen in the news before, are quite good for that. So I could say that this is 3,642 ones, or it's 364 10s and 2 1s. And there's many different ways that we can do that. So 3600s, 42 ones, and to explore that a little bit more. Another way of doing it, though, let's just say that I've got here 1, 2, 3, 4, 5, 6, 7. So I've got 7 ones, and I've got 8 10s and 3 hundreds here. Okay, so I would represent that as being, I know I've got 3 hundreds, 8 10s, and 7 ones. All right. Well, I can, as I've gone through and explained, you can write that in a number of ways. That could be 387 ones, as we know. That could be 38 10s and 7 ones, as we know. 3 ones. The limitation that I find for this is we can actually represent place value in another way. For example, I could say that it's the same as saying 200s, 18 10s, and 7 ones, which, as we know, is important for things like subtracting numbers and whatnot as well. So being able to represent that, I find that these ones here become a little bit more challenging when you're using these, whereas when you're using MAB, it becomes a little bit clearer to students. Okay, I've got 200s, 18 10s, and 7 ones. So once again, it's choosing which model to use or which representation to use, depending on what you're wanting to get from the students. These number expanders can be used for a whole range of things. MAB, I'm using it frequently with a whole range of different things as well. In terms of working with students, we'll come to show you how you can use it with multiplying, dividing, and all that in a little bit later. But the MAB is great for a range of stuff, but then it does have its limitations as well. So, the other thing with the MAB, the limitations in respect to that, is some people might be tempted to say, all right, well, let's use these for decimals. But that then causes misconceptions, because we've actually called this, students have grown up understanding this, or learning this to be 1, this understanding, learning this to be 10, and this to be 100. But if we start changing that and saying that this is 1, this is 1/10, and this is 1/100th, well, that's changed everything that they know to be true about this, and that's where the confusion kicks in. So there are other ways that we can represent these using or to represent decimal numbers using other models. And so therefore, that's where the limitation kicks in for MAB. MAB is great up until about 10, up to about 10,000. But then once you go to past tens of thousands, it becomes a bit of a challenge. Let me just move all this out of the way. And I'll show you some stuff in terms of that's helpful for decimals. So I find for decimals, something I created from going to Bunnings. And these here are just LAB. And what they are is essentially you just get some pipe and you decide whatever length you want it to be. Well, actually, no, sorry, there's another way of doing it. And that is, I've got to grab these first. So, for example, what happens is I start off with some washers and these become my thousandths. So what you do, obviously, is you get your 10 of these and you put them together. And so the washers are here. You put them together, make 10 of those to make a 100th. All right. And then you get 10 hundredths to make a 10th. And then you get 10 tenths to make you 1. And therefore you can use these for decimals. The advantages of this is, once again, you don't have to, you're not going to confuse students with the whole idea of MAB. A disadvantage of it, though, is that they only work linear, and that comes into play when it comes to multiplying them. So great for renaming and things like that with your tenths, your hundredths, your thousands, but really challenging in terms of for the multiplying. And I'll show you what I mean in respect to that in a second. And then the other thing with place value for rounding that I found through just doing this and exploring it somewhat is number charts. Now, as we know, I'm sure everyone uses number charts all the time. What I found, though, is with rounding in particular, that 0 to 99 charts really probably the way to go. And the reason for that, I'm going to show you something in terms of that comes from exploding dots. I'm not sure if people have seen it before, but exploding dots works like this. And it really is just to develop an understanding of place value or base, or it starts off as base 2 and works up to base 10. But I want to just show you how it works. So it's a 10 to 1 machine. And if I put a dot here, that's great. And in fact, I can put up to 10 dots here. So there's 5, 6, 7, 8, 9, 10. And as soon as my 10th dot goes in here, it moves over to here. So therefore 10 would be represented as being a 1 and a 0. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh, wait a second, there's 10 in here. And therefore it would be a 2 and a 0. The thing about this, and the thing about place value, is that it actually starts on the 0. Each of the levels that you get to, so 10, 20, or each place value that you get to, starts on the 0. So when we have a think about this, it starts when I know we count 1, 2, 3, 4, so it seems like we count on the 1, but we're actually starting on the 0. So what happens is the 10 really should be here, because that's the next time that we do the next dot, or that's the next time that the place value changes and goes up a level. So when we get this, what that actually demonstrates is if I'm rounding for 5, you can see here, if I colour in up to 5, well, you can see that naturally 5 will round up to 10 because it's closer to that end of the column. Same with if I land on 50. So if I've got 50 and I need to round up, if I just colour in all of that, you can see here that actually 50 is closer to the 100. That is, it's closer to the next place value. So this here, using a 0 to 99 chart, I found is much better for teaching the rounding than if we use this. And this is one of the limitations of MAB as well. Like if we have 50 here, well, it doesn't actually look like it would round up, because it looks like it's less than, or it's only half. It's not actually closer to it. But as we know, when it comes to place value, the next thing, or the next change in place value, happens when we get to the 0. And that's why we end up rounding up when it gets to 5. So hundreds chart. So I'm seeing here we have a hundreds chart at school where the 0 line is on the left. We don't like it, but are you suggesting that? So for me, yeah, when I'm looking at the rounding, absolutely, I think that the ones where it's 0 on the left does make more sense, and also, and because you can actually see what's happening there. We obviously see when we play games like Snakes and Ladders and all that kind of thing, that we start, or that has a 1, and that students are probably more used to seeing this. But I think conceptually what makes more sense, especially when it comes to rounding, is starting on a 0 and moving up from there. And I'm also happy to have people say, no, I disagree, and that's fine too. But this is what I've found through doing this. I'm actually able to justify and have students make more sense of what's going on intuitively through looking at something like this. The other thing as well, like when you start on Snakes and Ladders, or if I was taking a few steps, so if I said take 5 steps, I start on 0 steps. And as soon as I take my first step, I've actually moved 1 place. So we actually always start on 0, but we don't actually ever really count it out. So therefore the place value, as I said before, starts on 0. So therefore it makes sense to use a 0 to 99 one. And if you want to have longer, then make one that goes past 100 if you want. That's fine. But I find the 0 to 99 one makes more sense for things like rounding and whatnot as well. there we go. So in terms of the rounding, that's and the place value and things like that, there's a whole range of different things there. I've got some other ones as well. Let me grab these here. You may have seen decimats before. Here are some that I've laminated. I'd be happy to share these as well if you want to just grab them and print them out. But you can see here, if I call this 1, then I can call this tenths. It's clearly very different to this. I mean, it looks similar, but they're two different models. And because it looks different enough, we can then call, all right, well, this here is 1. I can then call this tenth. So if I color this in here, it becomes 3/10. So I might have 1 3/10, etc. And when does something like this become helpful? Well, it's when we start to look at multiplying decimals. And I'll come to that in a second. I'm just looking at the time. So I'll do some stuff around multiplication, and I probably won't get around to partitioning today. But I do want to touch on the different ways of multiplying and the different models that we've seen, in a range of different places that we can use, but the advantages and disadvantages of each. And this is certainly where I find some misconceptions start to form and whatnot. So first of all, let's start off with multiplying, say, 2-digit numbers. If I have this here, let's grab this stuff. So I've got my multiplication chart here, really complex kind of piece of technology. All it is it's a bit of laminated paper with a thing going down here. And we're going to use the area model to do this. We're going to compare it to some other models that you might have seen, whether it be on Facebook or the internet or whatever, and the algorithm, and then think about, well, what are the advantages and disadvantages of using each of these models, and when and why would you use it, or why would you not use it? So, for example, if I had something like, let's just say I'm going to multiply 13 by 12. All right, so I can represent, my question goes on the outside of these lines. So I've got 13, and I want to multiply it by 12. I've got something like that there. All right. Now, to figure out what the answer is, well, I've just got to figure out, well, what's going to go in each or in this region here. So what would the 10 by 10 be? Well, it would be 100. What would the 10 by 2 be? Well, that'd be 2 tens, wouldn't it? So we put the 2 tens in here. What would the 3 by the 10 be? Well, that'd be 3 tens. So let me grab a couple more here. And then what would the 3 by 2 be? Well, that would be 6. So I'll grab a couple more. Now, when I put all that together, so this part's my question, so I can remove that. So that is 13 times 12 ends up being 156. And we can see that quite intuitively in terms of what's going on. But what's actually happening here? Like, how is this actually working? Because we know if I went through and I did the traditional algorithm, that is, I'd do 13 times 12. Okay, so I do 2 times 3 is 6, 2 times 10 is equal to 20, so therefore 26. Or that's the same as saying 2 times 13, isn't it? And then I'd say 10 times 13. But this is what I learned growing up, and I wouldn't recommend saying it, but what I've learned growing up is, you just put a 0 there, and then you go 1 times 3. Well, that's 3, but it's not 1 times 3, it's 10 times 3, as we know. And 10 times 10 is 100, so therefore we'd end up getting that. And then we add them together, is 156. What's actually happening? How is this relating to this? Well, it's bringing in the place value that is so important to understanding what's actually going on when we multiply. That is, if we have a look here, I've got my 12 times my 13. Okay. Well, if I do 2 times 13, what I end up getting, so I've got to look at this and figure it out. So I've got my 13 is here, 10 and 3, and my 2 times my 13 is 26, which we can see here. All right. Then if I've got my 10 times my 13, well, that's going to be 10 times 13 is 130. And you can see that working there like that. And then when we bring it all together, it makes more sense. This here, what I find is when we have something visual to represent, it makes a lot more sense. And in fact, I'd rather this year, I actually rarely teach this. What I would go to, the only way that I would teach this is I'd show the kids, hey, this is one way that you might have seen it done before. How does this relate? And what I find is something like the box method to be a lot more helpful. That is, 13 is a 10 and a 3. And, 12 is a 10 and a 2. 13 is a 10 and a 3. Okay, so a 10 and a 10 is 100. A 10 times, or 2 10s are 20. 3 10s are 30. And 3 2s are 6. Can we see how these sort of come in to this here as well? I can see my 100 here. I can see my 30 here. I can see my 20 here. And I can see my 6 here. This here I find, and I've done this a number of times with students, especially in the tutoring, and these kids are pretty far behind when I'm working with them, but it doesn't take them long to go from seeing this to then being able to think about it in their head and actually visualize what's going on and come up with an answer without even needing to do this. Whereas when I show them this, or when I've seen them try and do this in their head, that's where mistakes will happen. They'll try and or they might forget to write the 0 or whatever it is when we know it's 10, but they might forget to do something there. Whereas when they visualize it, it's like that thing that I was talking about before with the paper mache. They've got something to attach it to make sense of it. And in fact, if we teach using these models, this can go a lot further. In fact, this can go all the way through to VCE and to year 9 and 10, where instead of calling it 13 times 12, we can say something like, and I won't go into it now, but it's the same thing works if I have something like that, which is year 9, year 10 maths. And we can use exactly the same kind of model or the same concepts and principles to be able to do that. So imagine if we're just teaching the students the one thing or the one concept or model, and it moves on moving forwards. Yeah. And so that is, algebra tiles is what we use for that. And they're so helpful. But then I was wondering for a long time, and in fact, it's only been in the last couple of days, well, how does this work for decimal numbers, right? Like, and because I can't use this as decimal, because as I said, we know students know this to be 100. We can't turn around and say, well, this is now 1, because it's just going to confuse them. So how are we going to make it work for decimals? Now, if I use these LAB, well, if this here was 1 and we had another one going down this way, I'd end up getting a square, and a square can't be 1 as well. It's got to be the same. It's got to be the same, right? So we can't use these LAB. This is a limitation of the LABs, and it's called linear. It's a linear arithmetic block because it's a straight line. It doesn't work where you're multiplying or you're coming up with an area region thing. It's okay if you're doing, say, 3 times 1.4, so you can have 3 lots of the 1s and 3 lots of the 0.4s and then do that. That's fine. But it becomes hard when you start doing, well, what's 1.3 times 1.2? And that's where something like this becomes a bit more helpful. Once again, using this same model. So if I had 1.3, well, this would be my 1. 1.3, and then I'm going to grab my 1.4. So I have 1 and 4/10, because 0.4. And it's important to use the place value language when we do this. So what am I going to get? Well, I'm going to go 1 and 3/10 times 1 and 4/10. Okay, well, what's going to be this high and this wide? Well, it's going to be a 1. See here how, unlike the LAB, we're able to keep the same size. This is 1, this is 1, this is still 1. It's not a different 1 as such. And then we can have, okay, well, 1 times 3/10. Well, that's going to get me 3/10. Goes there like that. Oops, I should color that in as well. So 1 and 3/10. And then I've got 1 times 4/10. So I'm going to have my 4/10 here. Like that. And then I've got 3/10 times 4/10. Well, there's nothing really here. I don't have, the tenths don't fit in there nicely, and they don't fit in there. So that's where I get in my hundredths, and I make that work. So I'm going to go 3/4, like that. So what do I get as an answer? Well, I get 1 3/10, 4/10. Okay, so that'd be 1 and 7/10. But then I've got 12 100ths. So it'd be 1 and 8/10 and 2 100ths, or 1.82, or 1 and 82 100ths. So you can see here that this same approach can be used in decimals, as well as algebra, as well as, you know, going back down to things like your regular multiplication. I find that this, having the one model, when you can do so much with it, is brilliant. But you've got to think about, well, what are the equipment that we use, and what kind of misconceptions might it form, what issues might come up with it, and what are its limitations as well. So I'll just about wrap it up there before I ask for any questions or anything along those lines. So as you've seen, I've just raced through a whole bunch of different representations, and there's plenty more. Like I've said, though, the whole way through, the three things that I think about are, what are its strengths? All right. So what are the things that it does really well? And every model will have something that it does really, really well. What are the limitations of it? So that is, I can take it to a certain point, but where does the model start to come unstuck? And what misconceptions, and this is the big one, is what misconceptions might it create in doing so? So and being aware of those so that we can try and navigate those so that we don't form these misconceptions within our students. So I guess to finish up, is there anyone who's got any questions? I've gone through a lot very, very quickly, and it's so hard when I don't have I don't have you in front of me. Is there anything at all in respect to any questions moving forwards?
Pop any questions in the chat, or open your mic if you want to ask something specific. I've got a few minutes left. Tom, I thought it was interesting too to see that you're making the links to, in a way, what some primary teachers are doing, that the kids need to be able to experience at secondary level as well. And I thought that was interesting as well at times there, to see what the secondary kids need to do and how it links directly back to the foundations that you are seeing taught in primary.
Absolutely. It's to have, if we can use the same kind of things and be consistent in how we go about it, and that requires work on the secondary teachers' part as well. There are a lot of secondary teachers that don't use algebra tiles to teach it. So it's about coming up with, it'd be great if you had a prep to 12 school and you could work together in this sense to go, okay, well, here's a model that can work across the board. Why don't we start to do that? And it really, through doing that, like I said, it's about that mathematical intuition. It's about building that sense of, it makes sense because I can see it, I can visualize what's happening. And what I've found, I'm doing tutoring at the moment, as I said, and so the kids coming into my group, and I've asked them, I said, oh, well, what do you think? I've got some feedback on them from the students, and they said, oh, the tutoring, it's interesting. I feel like it's a place to come and think, whereas maths is about just doing what we're told. Mm. And that to me said, okay, well, like, how using these manipulatives and getting students to actually make sense of it and use their intuition about what they see to be right and what they think to be right and make predictions. That's what maths is about.
Sure. Tom, there's a couple of questions there. One about sharing Decimat, but also Scott sent me a message saying it'd be good if you could provide links to some of the sources where maybe some of the templates can be downloaded, or these resources are, just so people sort of have a list of the types of manipulables you've shown, and links to some of those where they might get them from or find out more.
Yep, absolutely. And the other thing is, like, a lot of these ideas and that have come out of this book and the edition before it as well. So that's Teaching Mathematics Foundation to Middle Years by Di Seaman and the rest of the team there. Yeah, really, really quite helpful. If I was to recommend anything, it'd be, if I'm teaching a place value unit, grab the book, have a look at place value and how they suggest it, and you'll get a ton of this kind of stuff already, where the thinking's done for you too. But at the same time, still have a think about those three questions that I mentioned.
Yeah, Vicky's popped a link to some Decimat stuff in the chat, and I know Vicky's also got some great videos that she's made herself around using algebra tiles. So there's lots out there, and there's people here today who certainly have links to that stuff. So Tom, your PowerPoint and information, or some of those things, maybe we can add them to the event portal underneath your video once it's loaded up as well. If people come back in, they can find things later.
Yeah, and there is one more question here. The top 3 must-have manipulatives for grades, so lower grades, middle, senior. To be fair, it depends on what you want. It's so hard, but I would say for me, MAB just so helpful in terms of if you're going to spend money, MAB, yeah, and that for all of them. For the other ones, I would say dice, like 10-sided dice, because you don't have to come up with questions. Kids can roll dice and then come up with their own questions based on the numbers. I could roll a 13 and 12 or whatever, and then have to do that. And then once I've done it, I roll it again. So it's not about having a worksheet. The kids just keep doing more and more and more, and there's no end to it. So you don't have kids going unfinished because they just roll the dice and they have another go. It's about building that fluency. And then they've got agency as well, because they can choose what numbers and how they make them work. So dice, and the other thing would be whiteboard. So it's nothing too special, but yeah, something like the miniature whiteboards where you can write on would be the other one for me, and that would be the same across all year levels as well. And then it depends on specific what you want to make or what you want to teach, and think about that.
Yep, I've just popped a link to the book in the chat there. Somebody asked what was that book again. We do sell it on the Mav Shop on our website, where members can get a discount on that. It's also available other places, of course. All right, Tom, so thanks so much. We're just past 3 o'clock, and look, if anybody would like to join into the next session, which is just the optional one to have a chat, ask further questions, Tom will probably join us there, or you'll have to now, Tom, because I've said it. We'll be there for half an hour or so if anybody wants to pop in and have a chat, ask questions. I'd like to just thank you all for persisting through the day and sticking with us. The event portal will remain open till the end of the year, and the videos will be going up over the next week with PowerPoints from presenters coming in and being added. So don't check back immediately next week, but check back and we'll send you a message telling you when most of it's up there. If you need to contact anybody, you can't find their details, let us know and get in touch and we can hook you up. Hope you've had a fantastic day. It looks like it's gone well from our end. So we'll also send you a survey to give us some feedback. We hope that you'll join us next year. We may be back face-to-face. We may have a virtual component for regional teachers. We'll hopefully have both. But we'd definitely love to see you again and hope that you've had some great learning today. Cheers, everybody.